So the first interesting observation is that it's enough that we have just a generalized ordinal potential game. So let us have a generalized ordinal potential game and define another game when the utility functions are assumed to be the potential functions for each one of the players. So suddenly we have this game I said, remember in the example of identical utility game, when we have the same utility functions for all the players. In particular, that game itself is a potential game, of course, trivially, and here we create such a game by substituting all the utility functions, whichever they were, by the common potential function. And then the Nash equilibria of the new game are a subset of the Nash equilibria of the original game. In particular, if the new game has at least one Nash equilibria, then at least one Nash equilibrium, then so does the original game. Now, if the potential is not just a generalized ordinal potential, but a ordinal potential, then the sets of equilibria simply coincide. And the proof is simple. So consider a generalized ordinal potential. Then if you have an equilibrium in the game where we have changed, where we have replaced the utility functions with the potential function, then by the definition of an equilibrium, it means that for each player, for each strategy profile of the other players, or let's say for each strategies of the other players, and for each strategy to which this player can change, the no, there is a typo here. It's not for each strategies of the other player, it's for these concrete strategies of the other players, and for each strategy to which player I can deviate. 1 second, I need to fix that. Okay, so by the definition of equilibrium, if you have an Nash equilibrium, then it means that for each player and for each strategy to which that player could have deviated, the deviation would not have paid. So it means that the utility in the original profile would be at least as much as that player would get after deviation. Now, the game is the game where we have replaced the utility function with the potential function. So what we just said is that the potential in the original profile is at least as much as the potential when player I deviates to play Ti. To say that it's at least means that it's not strictly smaller. Now that, by the definition of generalized ordinal potential, means that the utility of this profile Si and Si minus I is not strictly smaller than the utility of profile Ti Si minus I. Because if it had been strictly smaller, then the potentials had been strictly smaller. That's the contrapositive. The contrapositive of the definition of generalized ordinal potential. And to say that the utility of Si minus I is not strictly smaller than the utility of Ti S minus I is the same as to say that the utility of SIS minus I is at least as large as the utility of TIS minus I, which is exactly, since it's for each player and each profile TI to which player I could deviate, exactly the definition of an equilibrium of the original game. So we have started the equilibrium of the game where we have replaced the utilities for potentials, and using the definition of Nash equilibria and generalized ordinal potential game, we have landed at the definition of a Nash equilibrium of the original game. So if you are an equilibrium of the game G prime, and here again it should be G prime after replacing the utilities with the potential, then you are also an equilibrium of the original game. Now, if the potential is not just a generalized ordinal potential, but it is a simply ordinal potential game, a full-fledged ordinal potential game, then the implication in our proof becomes simply an equivalent, and then we also have that a profile is a Nash equilibrium in the game where we have replaced the utilities with potentials, if and only if it's a Nash equilibrium in the original game. In both cases, if we have an equilibrium in the new game, it's also an equilibrium in the original game, which allows us to immediately conclude the following. The corollary is that if you have a generalized potential, ordinal potential game, where exists a generalized ordinal potential admitting a maximum, then the game has a Nash equilibrium. Why? Because such a maximum, by definition, is an equilibrium of the game where the utility functions are just potentials. And as we just have proven, the assumption that the game is generalized ordinal potential game implies that it's also an equilibrium of the original game. So this game has Nash equilibrium. And since when you have a finite set of possible profiles, then any function has a maximum on this set, in particular generalized ordinal potential function, and therefore we have another corollary, which is that a finite generalized ordinal potential game always has a Nash equilibrium. Okay. Now we've arrived at the important notion of path. It's not just a path on the graph; it's a path on the game between the various profiles of the game.